Now we're going to be looking at another way of using that energy. And I'm going to relate this idea in terms of water moving through some pipes. So in our first situation, what I'm going to do is create a large reservoir of water up here. And I'm going to be connecting it by a series of pipes to down here where it's going to turn a lovely little wheel before exiting the pipe. Our water is sitting up in the top here. It has the ability to fall down. At the moment, the tank is completely sealed, but it is held at a height above the ground. So our water here is existing with some height above the ground. It has the potential to fall. It isn't falling yet, but it has the potential to fall. What would happen once I make a hole in my tank? Right about here. What's going to happen now? It's going to flow through my pipe, down through there and across before coming in contact with my little spinny wheel. If I decrease the width of the pipe, what would happen to the amount of water able to go through? So the width of the pipe is going to control the amount of the water flowing through the pipe. If I want to make that little spinny wheel down the bottom spin faster, what should I do regarding the width of the pipe? If I have more water flowing through the pipe, there's more water that's going to push past my little spinny wheel, making it rotate more. If I have an increase in the width, I'm going to make the spinny wheel spin faster. What happens if I move my tank? At the moment, I've got it at the top of my pipe. What happens if I grab my entire tank and move it to there? Apart from cutting off the writing and now the ob is inside of the water tank, but what would happen to the spinny wheel at the bottom? It would slow down, right? The water inside of the tank has less distance to fall, our gravitational potential energy, mgh, as we have decreased the height, there is less of that potential energy there, so therefore, as we decrease the height, we're going to decrease the spin that is going to happen for our little wheel. So as height decreases, the spinning wheel will spin slower. I'm making these analogies because electricity is a little bit harder to understand in that regard. A lot of the time it is related to the idea of water moving through pipes, and that's what I'm trying to get the idea in here. Electricity, generally we have two different measurements that we're talking about. Our first measurement, or the first idea that we have, is the idea of voltage. And that is our water tank, is a potential difference. Remember in the initial situation of this, I had my water tank right up the top and the bottom of the tank was solid, right? So no water was able to go through. It still has the potential there though. The water still would like to not be a height above the ground, it would like to be on the ground. So that's why potential is there even though nothing is actually changing. It has the potential to do something. The other term that we use for electricity is current. Current is, in a sense, the idea of how much water is flowing through the pipe. The flow rate of the water, the number of charges that are moving through the pipe. If I close the tank again, it means that our current would go to 0, but we would still have a potential for that water to go down. And that's why if you ever look at a battery, so for example a AAA battery has a potential on it, it says that it is worth 1.5 volts. Because the charges still want to complete its transition around, it still would like to move, but it has no ability to make that movement. It isn't until that we connect it to a circuit that those charges are then able to move. For current, we use the symbol I. So our current is measured in amps. Now, it's technically amperes, but we actually just refer to it as amps, just as being that. And so that means that we get the unit of it being A. So voltage has a symbol of V that we use. We measure voltage in volts. And when we write volts, we write it with a symbol of V. Amps is our SI unit for electricity. Everything will be related to the terms of the ampere. However, that doesn't also make sense to me because the ampere tells us the flow of charges, right? So if we're looking at amps, our current is equal to the change in the charges over some change in time. Q here being our term for charge. Charge is measured in coulombs. Current, which is our SI unit, is a measure of the number of charges past a certain point for a period of time. So our voltage is equal to how much energy we are providing per charge on our charge again. What I have not talked about is this lovely little wheel down here. What could I do to my lovely little wheel to change it? I could make it heavier. I could make it lighter. I could give it more fins. I could give it less fins. All of these changes are going to affect how that water flows through the pipe. So it could make the water flow through easier, or it could make the water flow through with more difficulty. We call this resistance. Probably heard of the idea of resistance in many other situations, how hard it is to do something. You get resistance when you go and ask your parents, can I borrow the car? You get resistance when you go and ask your parents, can I have 150 bucks? The resistance is how hard it is to flow through a point. Our resistance is equal to, so our voltage divided by our current. And this has a law associated with it. Ohm's law. We are measuring our resistance in ohms, which is the capital Omega symbol. The next part of this is looking at how quickly that wheel is going to be spinning. So if the wheel is spinning very, very slowly, it's going to be using not very much energy out of the situation. It's going to have generally a lower amount of water flowing past. It's going to have possibly the height of our tank being lower. So the spinning of the wheel we equate to the power usage of it. So let's go and have a look at power. If we look at the spinning wheel, it's going to be spinning faster or slower. So it is going to be using a mixture of the current and the voltage. So let's put those together. And we are after power. So current, from our previous slide, we know that the current is the number of charges that are moving past for a period of time. So that is our Q on T. Voltage was a measure of joules per charge. And power is a measure of joules per second. So how could we make current and voltage combined together to produce us power? We would multiply them. Our charge of the current is going to cancel with a charge from voltage. Those are going to cancel each other out, and therefore we end up with joules per time, so joules per second. So we get that power is equal to IV. We also know that our resistance is equal to V on I. So if we are looking at a resistor, or we are looking at an item that is going to be using the energy of the circuit, we would be able to relate our resistance into our power formula. So if I rearrange my resistance formula and say that V is equal to IR, I would also have that its current, I, is then going to be equal to V on R. I could then grab those two relations, sub the V into there, sub the I into there, and I would get two power formulas out of this. I would get that power is equal to our current squared times by our resistance. And we would also have that our power is equal to V squared on R. Any questions for me? Because if there are no questions for me, that means there are going to be questions for you.